I have a set of design inputs for a torsion spring I'd like to make in CAD. I have wire diameter, coil OD, active coil count, 2 torque angles, and 2 arm lengths. Let's take this information and build a configuration-driven model. I'm going to start this model by just putting together a set of equations. So let's just begin by revealing the hidden items, which is the equations panel. So you can see it's now appeared. So we've got a set of global variables. So the first input is going to be the wire diameter, and I'm going to make that 1.5 mil. Now I'm going to input the overall diameter. That's 14 millimeters. Active coil count next. That's going to be 8.5. Shouldn't actually be millimeters, but I've added that anyway. We can remove that. Torque angle 0 degrees. The arm length 1 is going to be 15 millimeters. Oh, arm length 2, missed the A, and that's going to be 12 millimeters. Now we also need a reference mean diameter and mean radius. So let's start with the mean diameter, and that's going to be driven by the overall diameter and the wire diameter. So the mean diameter being the center of the center of the coil, and then the mean radius, which is half of the mean diameter. So here you have a set of basic inputs for the global variables, and we're going to base the rest of our equation-driven model around this information. So just remember the active coil count shouldn't be in millimeters. Let's now start building the model. So we're going to start by adding an axis. So some reference geometry, axis, and we're going to use 2 planes, the front and the top plane. And this is useful if you ever want to attach this CAD item to another model, so good to have an axis through the middle. And then we're going to draw on the right plane. We're going to put a helix in place, so centered by the axis. A reference diameter for the helix, which is going to be a mean diameter, so equals global variable mean diameter. So we're using our input straight away. So I've got my control variable, and now I'm just going to I'm not going to change the pitch, the revolutions, or the start angle. In fact, I might change the start angle because that's not in the right position. Let's just put that 180 degrees. This is where I want it to start. Okay, so we'll change the pitch and the revolutions elsewhere. So we're going back into the equations, manage equations, and you can see we've got a set of dimensions that have appeared, and this is what we've just input. So we need to edit this information. First of all, we need to figure out which bits are related to what. So let's see, what was that? Global variable. I'm going to associate this with the wire diameter. I could be wrong here. So let's just select the wire diameter. Click OK. That doesn't quite look right. Okay, let's go into the spiral. Okay, so the revolutions just changed to 1.5, so that's attached itself to the revolution. So I know. Let's go back into equations and we can sort this out now. So that was not the wire diameter, D5. That's the pitch. Sorry, that's the active coil count, not the pitch. So we're going to get equals active coils plus 1 over 360 times the torque angle, which is 0, because this is a free state we're working on at the moment. I'm saying 1 over 360 because I have a torque angle, and 360 degrees will equal 1 full rotation. So I need to break that torque angle down and convert it. And this might seem a little convoluted at the moment, and it just equals the active coil count that we've got written above. But later on, this will become really useful when we start to rotate the spring. So D4 becomes the wire diameter. Okay, so that looks more like the spring that we're looking to design. So we've got a pitch of 1.5, yep, so that's driven by the wire diameter. Revolutions of 8.5, which is controlled by our equations as well. And the 12.75 reference, if I measure the front and the back, this equals 12.75 millimeters long. So we've got control there, and that dimension is derived from the controlled equations that we've set above it. Okay, so we've got a controlled helix to base our coil bodies around. So let's just we'll build the coil bodies now. So on the top plane, at the start of our sketch, we need a reference to build our body. So let's constrain this circle by the origin. I need it a set distance. I need it the mean diameter, so equals global variable mean radius. Tick that, so that'll put it in exactly the right place. And it will always end up in the right position. And then this is our wire diameter, so equals wire diameter minus 0.0001. And that's important because that helps this helix to form properly. If it was the wire diameter exactly, we would start to see a few funny things happen. So I'm just going to offset it slightly. So this is our body coil wire diameter reference. Let's just make everything that we need construction as construction. It's not quite fully constrained. Horizontal is the wrong thing to use. Let's go vertical. So it's constrained by the start of the helix. So then let's build our main body. Sweep boss, the profile, the path. Let's build. This is the main body of the torsion spring. So we can go into the equations, and we've got everything's constrained, and we've got an extra equation or two at the bottom. Okay, let's start building our first arm. So we've got the body. Let's just rename it body coils. Okay, so now we need some reference geometry. So we're going to build 3 planes. The first one just attached to the end of this coil. And this is going to be our rotation angle 1. So then we're going to have a second plane which is going to track that first one and move with it. So it's attached to the axis, and the second reference is the rotation plan, and it's perpendicular to that plane. So it's going to move with it. We'll call this rotation angle 2. And we need one more. And this last plane we're going to draw on. We're going to sketch on, I mean. So just looking at what we've got, let's just reveal the mean diameter of the coils. Reference plane. So offset from rotation angle 2 by a set distance, so an arbitrary value, and then we can come out of here, go into the equations panel again, as we seem to. Let's just put this at an angle so we can see. So you can see it's just offset, it's in random free space at the moment. So let's just go to manage equations, bring that in, and the new dimension that's appeared at the bottom, so equals global variable mean radius, and that will bring it back into control. So you see the plane is now aligned with the mean diameter. So let's call this rotation angle 3. Okay, so these three angles are basically going to move together, and we need it to happen because this sketch that I'm going to build on rotation angle 3 needs to track the spring as it moves. So we need to constrain it against the wire diameter. So let's add a dimension here, or add a sketch line. Let's just find a comfortable position to start the sketch. So constraining it, both ends. And then we need some reference lines. Let's just bring it back to where we want it. Let's just go a bit closer in. Okay, so tracking that sketch. So we need a vertical line, a horizontal line. This is our construction geometry, and then this is going to be draw now. I'm going to draw, let's get rid of that. Now I'm going to draw the actual spring arm profile. Okay, so we need some dimensions. This will become clear in a second. Okay, so random arbitrary dimensions. So now construction geometry. Let's make this geometry construction. Everything basically except the diagonal line is construction geometry. Okay, so we need some dimensions now because this is not very well constrained. So equals global variables mean radius, and then its offset. So the length is driven by the first arm length, 15 mil. And the wire diameter, so equals global variables wire diameter divided by 8. Seems to not 2, 8. seems to align quite well. Okay. Okay, so we've got our constraints. I'm happy with this. Okay, so I'm going to show you why it's built the way it is with 3 reference planes in a second. So just so you can see, we've got our profile for building our arm. Okay, so if I were to create some configurations, so if I go, I've gone to configurations, if I go, so this is 0 degrees. 0 degrees is the spring is not loaded. And let's copy that configuration and make a new one at 50 degrees. So this would be the spring arm is loaded, torqued up to 50 degrees. So I've now got 2 configurations. And if I move the spring to a 50-degree position, which I will do in a second by going into the equations, manage equations. So I've got a torque angle here of 0, but I've set it to 50 degrees, so I want this to be 50. So 50 degrees in this configuration only. And if I switch between configurations, you can see that the arm is tracking the spring as the spring diameter increases as it's torqued up. So now we've seen that working, we can build the profile for the arm. So I convert entity, sweep, boss, the profile, the path, and if we switch configurations, I've got to turn it on. Always be careful to make sure, go to configure feature, make sure when you're working with configurations that you've not accidentally turned something off. So the arm is tracking the spring coil as it moves. And that's exactly what we want. And this is the reason why we've built so many equations around this model. Partly so we can move it and we can add additional configurations where it moves further, and partly so it's easy to edit in the future. So let's just group everything to do with this arm in one folder, and then we can move on to the final arm. And finish this model. Okay, so let's complete the final arm. So let's start by building some reference geometry from the front plane, an arbitrary value, into equations, manage equations, take that new dimension that's been added, equals global variables, mean radius, and that will put the new plane exactly where we want it. So let's start a sketch. Put in some reference guidelines. So some reference geometry, same as before. But this time it's going to be driven by the second arm global variable. So here is the length of the arm. Here's a template guide data. So equals global variables arm length t, which is not the same as arm length 1, equals global variables mean radius, and equals wire diameter divided by 8. Okay, so don't forget to make some of this geometry construction, everything except the length. Okay, now we can build our arm. So just a sketch for the profile. Now we can do a sweep boss. We selected the profile, we select the path, and we got a second arm. Okay, so that's the spring design complete. So let's just tidy it up, put the arm in a folder of its own, so when we come back we can edit it easily. And then you can see the geometry. Looks simple, but it's the equations that have helped us with this simplicity. So let's just finish off by doing some edits to show how this spring keeps control. Just make sure obviously anything new hasn't disappeared from configuration to configuration. Still moving. It's a working spring. Flicks between each angle. And if we were to add another configuration, so I really wanted this to go up to, I think it was 185 degrees I said at the start, so let's make that 185 degree configuration. So 185, this configuration only, tick. Okay, so now you can see the arm will move to 185 degrees. Zero, 50, 185. Okay, so let's just test these equations out and see how robust this spring design is. So let's just change the inputs. So the wire diameter, let's make 2 mil across all configurations. the overall diameter will change as well. Active coil count, yeah, let's change that. We can change the arm lengths. We could change the torque angle, but we've changed it so many times that let's try a few other things. So arm length 2, arm length 1. Okay, let's just 14 mil, that'll do. Okay, and this should completely change the shape of the spring, but it should still stay together. It shouldn't fail, it shouldn't alarm out, hopefully, when we press OK. Okay, so we've got a completely different size spring now. And it should still track the configurations. Let's try something wacky, something completely different in the equations panel. See what that does to the spring. So even when you come up with a ridiculous size, it still tracks. There you go. A really small spring. So this is why we put all this detail into the equations, to make sure that we can completely control this spring, no matter what we throw at it.